to begin, we should talk a little bit about elements. When we're talking about elements here, what we're talking about is a pure substance. And elements are substances that are made up of only one kind of atom. So all the atoms are going to be the same. So when we talk about the element of hydrogen, which is this one right over here, then what we're talking about are all hydrogen atoms are the same. They all have the same basic properties, and that basic property is the number of protons. Now, this is the periodic table. You can see here, it's lined up by periods, which are going to be these guys here that go across. So our rows are going to be the periods. And they also have columns, and they represent different things. The periods are going to represent the electron level, or the energy level for the electrons, and then your groups are going to represent the number of valence electrons per se, and that's how they react with others. So that's the real simple way to look at it that way. Okay, and you'll learn more about the periodic table in the lesson this unit. So when we talk about elements, we say that they all have the same atom. They all share the same, they all look the same, it's that way. So that's kind of what we're talking about here are our atoms. And if you can recall back, an atom is made of primarily two parts. We have this nucleus here, which is in the inside of the atom, and that's where we find the protons and the neutrons. And then orbiting around in these energy levels, and this is what the periods were for the periodic table, we can find the electrons for an atom. So if we recall back, we have our protons, which are going to be these guys here, and our protons have a positive 1 charge, and their mass is 1 atomic mass unit, and they're found in the nucleus, and they're represented by these red circles in here. We also have neutrons, and neutrons are called that because they have no charge. They also have a mass of 1 atomic mass unit, and they're also found in the nucleus, and those would be the little blue ones in here as well. And then we end up with our electrons. The electrons have a negative 1 charge. Their mass is 1/1874th of a proton, so they're really negligible. They really don't count. And these are the ones we find in these energy levels or these orbitals out here. Okay? When you look at the periodic table, you're going to see each element's going to have its own box here, and each of the things inside kind of tells us what it is. We have our symbol, which is a shorthand version of writing down which element it is. And then we'll have the common name as well. Those ones you can see. For this one, we have a symbol of C, which represents carbon. They're going to have an atomic number, which is going to be the number of protons. And in a neutral atom, it's also the number of electrons. But primarily, we want you to focus down that it's the number of protons. And then we have a bigger number down here. This is going to be the atomic mass. And this tells me the average mass of that element. And it's primarily the number of protons and the number of neutrons. So that's what we need to know about atoms moving forward. Okay, for an element, we can't take an atom and we can't change the number of protons. If we change the number of protons in an element, then what we're doing is we're changing the element it is. So in our example here in the pictures, we're looking at carbon. For all of our carbon atoms, you can see here, they're all going to have 6 protons, and that's what defines it as being carbon. We can change the number of neutrons. So when we change the number of neutrons, we create what we call an isotope. And an isotope is just going to be an atom that has a varying mass number. And the reason the mass number changes is because we have different number of neutrons. The proton stays the same, that's what makes it carbon, but the neutrons can change its atomic mass. If we look in the most common form of carbon, it's going to be this carbon-12 here, we'll notice that there are 6 neutrons here. If we go to carbon-13, which is also stable but not as common, we know there's still going to be our 6 protons, but now we have 7 neutrons. So it's going to be a little bit heavier version. And then we get to our fun little buddy over here, this carbon-14. And carbon-14, because it's carbon, tells us we have 6 protons, but we're going to have 8 neutrons. Okay, and this one is radioactive, it's unstable, and this is what we use to date modern things. Anything to about 50,000 years ago, we can use carbon-14 dating on. But isotopes are just going to be varying mass numbers of an atom. It's the same element, though, because remember, it maintains that same number of protons. Okay, so we just learned that you can't change the number of protons, but you can change the number of neutrons, and that's what makes an isotope. You can also change the number of electrons. And when we change the number of electrons, then we create what we call an ion over here. Okay, and our ions are quite simply just a charged atom. Okay, so we charge it by removing or gaining an electron. So we'll look over here and we'll see here that we have our nucleus and we have our orbiting electrons. We have an electron here and an electron here. And then if we take this electron out, we end up with what we call a cation. And a cation has this little T, so you can remember that little T tells me it's going to be positive. And the reason it's positive is because now it has more protons than electrons, so it has a net positive charge, and that's why we call it a cation. We can do the same if we add an electron. Then we end up with an anion, and an anion has this N inside for negative. So these are going to be our negatively charged ions. And you can see that down here. If I lose an electron, now I have more protons. It's positive, and it's a cation. If we gain an electron, we have more electrons, so it has a net negative charge, and it's going to be an anion. And we can see that happens here with sodium chloride. And we'll talk about sodium chloride a lot in this class. But see our sodium here, we're going to take this single solitary electron and we're going to give it to chlorine. Chlorine has one empty space. You can see that empty space is right down here. So when we put this electron here, we end up with a full outer shell, but a negative charge. And we have a full outer shell here because we dropped down one. Now we have a positive charge because we have more proteins, and the positive and negative attract each other, and that's how we form sodium chloride or salt. Now, we talked earlier about elements, and we said that elements have one kind of atom, and that means that all the atoms are going to have the same number of protons. We can also make what we call compounds, and compounds have two or more kinds of atoms. Okay, so we can have an element, we have helium here, which is a single atom, or we can have oxygen, and even though there's two atoms, we notice that they're the same, that's why it's still an element. When we get into the case of water, notice how water has both hydrogen and oxygen. So we have two different kinds. That's what makes it a compound. So remember, a compound has two or more kinds of atoms. If it's just one kind of atom, it's still considered an element. Now, jumping back to electrons again, we're going to talk a little bit about what we call valence electrons. And valence electrons are the ones in the outer shell. And we kind of hinted at that when we were looking at ions. And valence electrons determine how it's going to bond or react with other elements. So we can see in our group of the periodic table, in group 1, we have one valence electron. In group 2, we're going to have two valence electrons, and so on and so forth as we go across. Now, group 3 is going to have 3, but then we jump to 13. And the reason we do that is because we generally tend to focus more of our attention on the first 20 or so elements to show us how these work. So 13, get rid of the 1, we have 3, 14, 15, 16, 17, and then group 18, these guys are going to have 8. Now helium only has 2 because it's in the first energy level, and that one only holds 2 electrons. But these ones are going to be full, and these are where we call our noble gases or our inert elements. And these are the ones that because they're full, they generally tend not to react. These that are missing a space from 8, so they have 7, they're going to look to gain an electron, and these guys here that have only 1 electron, they kind of want to get rid of that one. So we'll talk about bonding a little bit more in the lesson, but I just wanted you to get an idea of what we call valence electrons, and those are the outermost ones. Now there's 3 primary types of bonds we'll talk about in the course. The first one is going to be ionic, so we can pretty much tell that we're going to be dealing with ions. So if we remember back and we look at sodium, sodium had 1 valence electron out here. And we have chlorine. Chlorine has 7 valence electrons, but it has this little empty spot over here. It'd like to have a full complement of 8. What they'll do is the sodium will give up its electron, and when it gives up its electron, it now has more protons, and now it becomes a positive ion. The chlorine's going to gain this electron, so now it has more electrons than protons, so it has a net negative charge, and we get this ion. And then the positives and the negatives, the positive in sodium and the negative in chlorine, they're going to attract each other, and that's how we form table salt down here. And you can see another example here. We have calcium that has 2 valence electrons, and it's going to give 1 to each of these fluorines, and then we end up with calcium that has a +2 charge because it's going to have 2 more protons than electrons, plus each of these fluorines, which are going to have a -1 charge. So 2 minus 1 minus 1 is going to be 0, and that's what's going to make this an ionic compound that's going to work. So ionic bonds are when we form ions, so we have a positive and a negative ion, and those two are going to attract to each other, and that's how we form those compounds. Okay, the next type of bond we're going to talk about are these covalent bonds. And covalent bonds differ from ionic bonds. In ionic bonds, if you can recall, we gave away or we gained electrons and we formed ions. In covalent bonds, we're going to share these electrons. So what we'll notice is we'll take this hydrogen first, and our hydrogen, each one is going to have 1 electron like so. The oxygen over here is going to have 6. So this is going to be 2, 3, 4, 5, 6. Now, for oxygen to be happy, it wants to have 8 total electrons around it. For the hydrogens to be happy, they want to have these 2 electrons around it. So what they end up doing is they'll end up sharing this pair. So when they do so, that means oxygen now has 8 at any given moment, and each of the hydrogens will have 2 electrons at any given moment. Now this is what makes it a covalent bond, and because they're sharing the electrons, they tend to be a stronger bond. Okay? So that's the difference. Ionic, we give up the electrons. Covalent, we share the electrons. Okay, the third and final type of bond is this metallic bond. And metallic bonds deal with metals, and we can see it's kind of ionic. These metal ions are here, and they release these electrons. And these electrons kind of just pool around all of the different ions, and they can move back and forth, they can flow around, and that's what makes it a little bit of a different bond. The benefit of this is that if I send electricity through it, we can put all these little electrons into motion, and that's how we get a current. So metallic bonds allow us to have things like wires and things of that nature. Okay, so that's it for this video. As always, good luck with the lesson, and we will see you in the next video. So, what makes a mineral? Basically, they have to have 5 different things about them, and if all 5 of those criteria are met, then it's considered a mineral. The first is it has to be naturally occurring, which means that we find it out in nature. It can't be made in a lab. It has to be found in nature. We can recreate it, but it's not a mineral unless it's made in nature. It has to be a solid, so liquids and gases don't count. It's only solids here. It has to have an orderly crystalline structure, which means that it's going to have a crystal shape to it, and how it lines up is going to be based on its composition. Now, speaking of composition, it's going to have a definite chemical composition. So all samples of a mineral are going to be made up of the same elements, the same ratio. So it's going to have the same chemical composition. And then finally, they're generally considered to be inorganic. And we'll talk about in the lesson a couple of them that are organic in nature. But for the most part, that means they do not come from a living thing. Okay, so for it to be a mineral, it has to have all 5 of these characteristics. Okay, so now that we know what a mineral is, let's talk about how they form. Minerals are going to form by 4 basic processes. The first one is going to be this crystallization from magma. If you can recall, magma is going to be molten rock, molten material that way. And as it cools, these things are going to crystallize out, and that's how we get these minerals. So depending on the composition of the magma, the rate of cooling is what mineral we're going to get that way. We also can have precipitation, and that means that if we have some mineral things suspended in water, so we have our water here, and you have some mineral products in here, as this water evaporates out, okay, as the water evaporates out or gets boiled off, then what's left behind is going to come together, and that's what will form a mineral that way. So we can form it from precipitation that way. We also have pressure and temperature. So under extreme pressure, we can squeeze these atoms together, and temperature can provide the energy needed for the reaction to occur, and we can form new minerals that way. And then finally, we have hydrothermal solutions, which are really hot liquid solutions, hot water basically. And that's going to kind of work like the precipitation and the pressure and temperature together, and it's going to just bring these hot solutions together, and the reactions will happen that way. So we talked about what a mineral was. Now we know how they form. They form from these 4 basic processes. Okay, the last thing I want to talk to you about are mineral groups, or basically how do we classify minerals. And we classify minerals based on their composition. What are they made of? What elements can we find inside of them? The most common one are the silicates here, and the silicates are called that because they're made with silicone and oxygen. All right. The next common are going to be our carbonates, and our carbonates have the carbon and oxygen here. We also have oxides, okay, and our oxides are simply because they have this oxygen. We have the sulfates and sulfides, and as you can guess from the name, these guys are going to have sulfur. We have our halides, which are the halogens, and the halogens on the periodic table are one of the last groups. And we'll see these ones here, they all have one of these halogens inside of it. And then finally we have the native elements. And the native elements is where it's an element by itself, and primarily the ones we know familiar are going to be like silver and gold, carbon in the form of diamonds, so and graphite. So we can see when it's just the element, it's going to be called a native element. It's classified a little different. Okay, so that takes us to the end of our video. As always, good luck on the lessons, and we'll see you in the next video. Okay, so the first property we want to talk about is color. And color is simply what color is the mineral that we're trying to identify. Color is probably the worst trait to look at because you can have a little bit of impurities, and those impurities will change the color of the mineral. So we generally try not to use color. It's a good starting point, but it's not something that's going to be really good to use. The type of color that is good is if we use something called streak, and streak is going to be the color of its powdered form. So if we look down in here, this picture, you can see that hematite has kind of a reddish-brown streak, and magnetite is going to be kind of a grayish streak. And we get the streak by taking our mineral substance and just kind of basically rubbing it on this unfired piece of porcelain, which we call a streak plate. So remember, the color of the powdered form is going to be better than just the color of it. Now, we also have another term called luster, and luster is simply how light's reflected from the surface. So we can kind of see some examples here. We have metallic here, we'll have a silky kind of reflection here, you'll have a dull one, kind of looks greasy, so kind of just how it basically, the light is reflected from the surface of it. So that gets us our color, our streak, and our luster. Another good property to use is crystal form, or which family is it in. This is really a good one because remember, as a mineral, it has to have an ordered crystalline structure, and this is what forms the crystal form for it. So we can kind of see there where it's important. The problem is that for you to get the perfect crystal growing, you have to have something that is unlimited in space and unlimited in supply. So if there's other rocks around and you're growing a crystal in a small area, it's going to bump into the rocks, and that's going to change its shape because it's kind of compressed and it's kind of isolated in there. So if we can grow one that has it, then we can use its crystal shape to help us out. One of the better properties to use is what we call hardness. And hardness we rate on the Mohs hardness scale, which you can see here. It goes from 1 to 10, and quite simply the numbers tell us kind of how easily it is to be scratched is what we talk about. So we start down here with talc and gypsum. Those are going to be really easy to scratch. They're kind of easy, delicate minerals, all the way up to diamond, which is the hardest natural substance that we know. And that one's very difficult to scratch. In fact, it's really easy to scratch other things with it. And that's how you test for hardness, is you'll take like a piece of gypsum and scratch a piece of talc, a piece of calcite will scratch a piece of gypsum, a piece of topaz will scratch a piece of quartz, and so on. Now there are some common objects that we use in the testing just so that we can kind of see what the difference is. So your fingernail's at about 2.5, a copper penny's at about 3.5. So you could take your fingernail and scratch gypsum and talc, but you would not be able to scratch calcite because it has a 3. We have a knife, we have our steel nails, and like a masonry drill bit. So you can see just by testing to see which one it scratches or scratched by it, that's how we can determine hardness. And this is a really good indicator of what mineral it is. Now the next two terms we're going to go over are cleavage and fracture. And these deal with how a mineral breaks. When we have cleavage, what we say is that it's going to break in one direction and form a flat surface. So if we look at muscovite here, you can see it breaks off in these little sheets, and you can see that it's a flat surface. We can have it in 2 directions like feldspar, 3 directions like halite, 3 other directions in calcite, but you see that all of these are going to have these flat surfaces to them. And that tells us that it's cleavage, if it's a nice even flat surface. If it doesn't break that way, then we define it as having fracture. And you can see in the rocks shown down here that they're all just kind of mumbly-jumbly and broken apart. There's no real flat surfaces. I mean, you can find tiny ones, but overall there's no big flat surfaces like you would see here. All right, so cleavage is if it breaks on a nice flat surface. Fracture is if it's an uneven breaking. Now, density is a really good way to identify the mineral. Density quite simply tells us how much stuff I have in a certain amount of space. And you can see that this one here is going to have more stuff in the same amount of space, so it would be more dense. We calculate density by finding its mass on a balance scale and then finding its volume. We take the mass divided by the volume, and that's what gives us our density ratio. So density is really good. It helps us out in identifying which mineral because they all have a varying different density, and we can find simple little subtle differences in density a little easier than, say, hardness or luster. And then we have some other properties that are out there. Some of them, by the way they touch, they feel. Some may feel greasy, some may feel slimy. Malleability, they're easily shaped. If you take gold, you can change the shape of it, so it's malleable. Metals, you can do this. Some of the other ones, if you smashed a diamond with a hammer, then it would just shatter, whereas if you smash gold with a hammer, it'll flatten out. We have magnetite and hematite, which are going to be magnetic. Hematite is magnetic. You can pick it up with a magnet. Your magnetite is going to be actually a magnet, so you can actually pick up small paper clips and things that way. Some of them will have a distinct smell. Sulfur is a really good example of this one, where when you scratch it with your fingernail, it smells like rotten eggs. Some of them like taste. Your halite, okay, which is your salt, you'd be able to taste that, but I don't recommend going out and licking rocks. And then we have some optical properties. If we look at calcite over here, calcite exhibits double refraction. So you can see that if we take a piece of calcite and put it down on words, we're getting two images formed, and that's what that double refraction is. Okay, so that was a quick overview of the properties that we look at in minerals to identify them. The lesson will go through these in detail, and then we also have a lab coming up where you'll get to practice identifying which minerals are which. All right, as always, good luck in your lessons, and we'll see you in the next video.